Great. Well, those meetings you are hosting. One more minor. Yeah, please. There we go. Thank you. Apologies for the technical delay to you guys and to the audience.
Okay, welcome everybody. Today we have Cameron Wake, a research professor at the Institute for the Study of Earth, Oceans, and Space here at UNH. He leads a research program investigating regional climate change through the analysis of ice cores and other instrumental data. He'll be speaking about data obtained from ice cores in Denali National Park.
Thanks, Lynette. I'm surprised at the turnout. I thought everybody would be on the sort of AGU getaway day, but so thanks for sticking around. I was really torn on what to talk about today. We have a whole new set of downscaled climate model simulations that project how climate's going to change across New England. I've been working on that with Liz Burakowski, and I thought that would all be ready to show, but it's not. So I'm showing you way more interesting stuff from Alaska and bringing in the ocean a little bit more. So that was, I'm happy I came down on this side. So I want to talk to you about an ice core project that I've been working on. I started back in 2005 when I first went to Alaska and flew over the Alaska range in a little plane and said, we have to come drill here. Over that time, actually with this round, 9 National Science Foundation proposals, 3 of which have been funded. It's been a really long-term project, but we pieced it together and really has been a deep collaborative effort with my colleagues at Dartmouth and University of Maine, and especially Eric Osterberg, Dom Winsky. Dom got his PhD as part of this project from Dartmouth, and Carl Kreutz and Seth Campbell from the University of Maine, and all of it funded by the National Science Foundation. Before I dive in, I want to give a plug for an effort that several of us at the university have been working on to essentially develop a strategic research strategy for the university focused on the Arctic, and then broaden that out to include a whole bunch of research institutions and other institutions across New England. So hopefully you all know that the Arctic is changing dramatically. There's a lot of new federal funding for essentially navigating the new Arctic. And we think that New England has a much bigger role to play than it currently does in better understanding that change in the Arctic and what it might mean for the people that live there. So we got a small grant from the National Science Foundation, a small grant from UNH from one of the core proposals. And we are building this Arctic network across New England. You can see our primary goal here: foster connections and research collaborations amongst people working and living in the North Atlantic Arctic. The rationale here is that much of the United States focus is on the Alaskan sector of the Arctic, and there's lots that need to be done in the North Atlantic Arctic, and why not have us do it? There's lots of great research at UNH. I would say that we are less than the sum of our parts because we have not collaborated in big, significant ways. If you want to, not if you want to, we would love for you to be engaged. Jack is a key part of the team, but lots of other people on campus. As one of our colleagues might say, we are already a network because we have a web page. And we've got some minimal funding. So we're the New England Arctic Network. That's the URL. If you're interested, please get a hold of me or Jack or Kathy Duderstadt, and you'll start getting lots of emails from us in our monthly Arctic newsletter, et cetera. All right. So I want to talk a little bit about why ice cores are great paleoclimate archives. And that picture really sort of explains a lot of it to me. It's actually from Antarctica, but it'll do the trick. It's a snow pit that's been dug in the snow, another snow pit behind it, and the snow pit this gentleman standing in has been covered so you can see the backlighting, and you can see those beautiful horizontal layers. So when we look for places to drill ice cores, we look for glaciers that have these beautiful horizontal layers, not just on the surface, but going back in time. And this is about 1 year of snow accumulation to here. So this is Antarctica, that's pretty dry. And the records I'm going to show you, we get on the order of sort of 1 to 1.5 meters water equivalent of snow. So think about like 20 feet of snow per year. So we're getting really high resolution records. We sample this and commonly on the surface at 5 to 10 centimeter intervals. As you go deeper, we sample it much more finely. But it's really these high resolution records of which you can measure many, many, many things, of which I'll show you some today. The other thing, well, I mentioned we look for that horizontal stratigraphy that extends all the way down through the glacier. So here's an idealized schematic view of a really big ice cap. You sort of think of that as like Greenland. If you go right up to the top of the Greenland, where Jack helps run the summit station, really there's almost no horizontal velocity. All the velocity is vertical. You get thick layers at the surface, but as those layers go further down in the glacier, because snow falls on top, you actually get these flow patterns where those layers actually thin as the glacier flows horizontally. Where you don't want to drill a core is over here, because when you get down here, you're actually sampling snow that fell on the surface. So we often look for these divide sites. And historically, those divide sites have best been captured in big polar glaciers. More recently, we're finding a few on alpine glaciers around the world. So this is where we chose to drill our core. We did 6 or 7 years of reconnaissance to find this location. This is we're at the medical camp on Denali here, so 14,500 feet. There's a medical camp run by the Park Service. We're looking across at Mount Hunter. There's the main peak, there's the secondary peak, and that's where we drilled our core, and I'll show you some other pictures of that. If you look at the cross section, you can see where we are in Alaska up there on the Alaska range. That red line represents the elevation gradient from essentially the Gulf of Alaska going all the way up to the North Slope. You can see that the Alaska Range really actually sits in a place where it is a big physical barrier to moisture coming from the Gulf of Alaska. I'm going to talk a lot about that. That one of our main stories is that we've seen significant changes in precipitation, and you would expect to see this at this first big orographic barrier coming in from the Pacific Ocean. So as I said, we did lots of years of reconnaissance, which is the real fun part. You get to fly in there and climb mountains essentially. Lots of hauling. This is the Calhitna Glacier heading up towards sort of on the main climbing route going up to Denali. We did a lot of shallow cores to start off with to ensure that we could actually pick up a really good seasonal signal. So we, dig a 6 or 8 meter snow pit, and we drill as far as we could with this manual logger, and we pull all those cores out, and we bring them back frozen, and we test all our logistics. For us, this reconnaissance time was really important because it allowed us to establish a really good working relationship with Denali National Park. When we first got there, they really thought we were affectionately called, right, beakers. It's like, these guys don't know what they're doing. We've had probably amongst us many decades of alpine experience, but we had to develop that relationship before they were willing to commit resources to work with us. And that commitment really came in the way of, we operated jointly meteorological stations, which were really important, but they had access to a helicopter, which we needed to get to the best place to drill. We also did a lot of, so in addition to drilling the cores and bringing them back and analyzing them for a bunch of different chemical constituents, we also did a lot of physical surveys. This is one of our team dragging a GPR, which essentially just sends an electromagnetic wave down through the glacier, bounces up off different horizontal layers within the glacier, back up to the surface, so you get a sense of what the internal structure of the glacier is like, which is critical if you're going to find those areas that are really flat all the way down to the bottom. And then this is actually a picture coming from that last site. We went to a bunch of different locations, and one of the locations we looked at this glacier and said, there's a divide site that we have to drill at, and we can't possibly get there because we don't have the helicopter. This was sort of our first reconnaissance season. But after several reconnaissance seasons, we got Denali National Park engaged, and we ended up essentially using their helicopter for free. You can get there by climbing, but you can't get there with all your equipment. So here's a really quick summary of some of the geophysical findings of the site. So I'm on the south peak here. We're looking at the north peak, and then the big Denali Massif is over on this side. You get a sense it's a pretty small glacier. It's constrained on the north and south sides by bedrock, and then it flows sort of to the east and the west. And just like a big ice cap, those ice they just fall off. They just calve off onto the glaciers off really steep cliffs. What you can see here is the horizontal structure within the glacier itself, and we're looking at this line right here at EW1. So this is the upper 100 meters depth, and you can see, right, you can see sort of the fern at the top and lots of reflection layers. But you can see this really nice horizontal stratigraphy that goes all the way down through the top. And actually, if you begin down here, right, we're down, our cores were about 208 meters. We drilled right over here. So it's pretty good result, but nice horizontal stratigraphy throughout the entire glacier. That was really important. I'll also mention that the results I'm going to show you are from the upper 198 meters of the core. So the layers are so thin when you get down on the bottom 10 meters of the core, we didn't want to sample them until we could sample them at really high resolution. So we met the key objectives of the proposals that we wrote to the NSF, but now we've written more to analyze those lower 10 meters. We think we might have, so the records I'm going to show you are 1,200 years old. We might have an entire Holocene record in those bottom 10 meters, but we want to be sure we do a really good job at sampling it when we start cutting it up. And then over here, you can see same thing. So the pictures from down here, right? You can see the deepest area right here in the middle of the glacier at 200, little over 200 meters. So here's the video that I can't make work on this computer. So just bear with me because I've brought it up on a web page. Do we have any audio? Doesn't matter, it's not big audio. You guys can see that okay? So there's a shot of our drill site. We did a lot of skiing. We were up there when there was sort of lots of light, so we'd work our 12-hour days and then we'd go skiing in the evening. That was the Denali National Park helicopter that really was critical to all of our logistics. It was only a 5-minute flight in from base camp to get to our site, which is about sort of like a 3 to 4 day climb if you're a good mountain climber. This is the drill site. We did our entire drill with solar panels and wind power, so we didn't burn any fossil fuel. We burned lots of fossil fuel in the helicopter, so it wasn't carbon neutral. There's the lightweight drill that we assembled up there. You get a sense of the sonde. And this is a pretty small system, so we drill 1 meter sections at a time. And pull the barrel out and then pull the core out and then send the barrel back down. Pack all the cores in, measure them, weigh them, pack all the cores in these insulated shipping containers, put snow and ice in them, keep them in snow caves, and then when we were ready to head out, we just loaded them onto the planes that came into base camp, right onto 2 freezer trucks that were sitting in Talkeetna. They kept all the cores frozen and then drove them down to Denver to the National Ice Core Lab, where we processed the cores and then we shipped the samples to UNH and Dartmouth and UMaine for the analyses. And there's all of our work just disappearing into the clouds, which caused for concern at some point in time. But we got them all back safely. Right, so I go down here for PowerPoint. I will share one story with you. We wanted all sort of the young bucks on the project to stay and drill the core once we got everything set up, because we wanted to maximize the potential for the core being recovered and maximize our time up there. So once we got the field camp set up, only 4 people remained and everybody else left. So I was back here sort of in my shorts in the spring in New England, and I got a call from the freezer truck driver, and he was from Tennessee or North Carolina. He's like, "Hey, where am I going in Alaska?" And I said, "I'm sorry, like, aren't you on the runway?" He's like, no, I can't find, I don't even know how to pronounce the name of the town you're sending me to. So luckily I had his phone number, and it wasn't one of the guy's cell phones on the mountain. It didn't work, and I ended up being able to get him on the right turnoff off the highway. So again, solar panel and wind, and that's just the image of our drill and our wonderful driller from IDDO at University of Wisconsin. So we drilled 2 parallel cores to bedrock, analyzed both of them to compare the records and ensure that sort of the contamination was not driving the signals that we see. Then last photo, this is the best day in any driller's life, is when you start seeing the cloudy ice on the bottom of the glacier, because you know you're very close to bedrock. So this was the last piece of core that we pulled up, and these pebbles are telling us that we're very close to the bottom. So knock on wood, it means you've got the core, right, and you haven't lost your drill song. So we brought those cores back. We analyzed them for a whole bunch of chemical constituents. I won't go into all those details unless you want me to. One of the things that's really fantastic about this core, and I mentioned it already, is that there's so much snow accumulation that we get really high resolution signals. So what I'm showing you here are records from 2010 back to 1970. So you got 40 years of record. Stable isotopes, oxygen isotopes at the top, magnesium, which is a strong indicator of dust. These are actually dust particles that we're measuring. So the magnesium is going to be the soluble component of the dust. This is going to be the solid component. Ammonium, which really represents sort of ecosystem activity, and MSA, methylsulfonic acid, which is a tracer for ocean biological activity. What hopefully you see from this image already is these really strong annual signals that we have in this core. So the main way that we dated this core was we counted back annual layers in literally dozens of different chemical species. And because we had different chemical species with different sources, there's different timing, we were actually able to identify summer and winter layers in this core. So to take that one step further, you can see up here, oxygen isotopes, magnesium peaks in the spring, really big dust storm events that happen in Central Asia that bring dust across the northern Pacific Ocean. We've got the dust again, the ammonium summer peak, and the MSA fall peak. And counting these with one of these parameters can be a little tricky, 2 parameters, But once you're getting up to 5 to 10 to 15 to 20, we have really high confidence in our dating, at least in the upper 100 to 120 meters of the core, where we're, 120 years of the core, where we're comparing these records to instrumental data. It's really important that we match it for the exact year. And I want to say this is the first core that I've worked on that we're really confident that we're matching year for year. So we're maybe off by a couple of months in the dating going back in time. But the dating control on this is really specific. So not only did we use the annual dating control, we also used this wonderful reference horizon, that's sort of human-driven by testing of nuclear weapons in the atmosphere. So these are the tests. There were a whole bunch of tests in 1954 before there was a nuclear test ban, and then another whole set in 1962 before a 1963 test ban. So that radioactive material went up into the upper troposphere, the stratosphere, went all around the world and came down, and we now use that to date our cores. So we used Jack's radionuclide lab over in Morse Hall, collected a bunch of samples. You can see the increase in 1954, and then this huge increase in 1963, which is pretty typical. We do this on glaciers around the globe as sort of unambiguous tracers of those particular years. Then we also use a lot of dating looking at, this is the sulfate record, so big peaks being driven primarily by big volcanic eruptions. Really big one, right, Katmai in 1912 was just around the corner. There's a huge chloride spike. That's another sort of record deep in the, signal deep in the core that really helps us clearly establish these depth-age relationships. So we counted back independently of these, and then we can go back and say, well, when we counted back, did we hit this target? And if we didn't, we have to go back and recount again and figure it out and make sure that we hit that 1912 year. All right, so we have this really good depth-age relationship. And what you'll notice is that, right, most of the core really represents just like 100 years, a couple hundred years. And really, when you get down here, you can see that there's that really significant layer thinning. And that comes into significant play when I'm going to talk about reconstructing snow accumulation rates. All right, so on to results. Before I get to the ice core results, I just want to, if you don't know much about North Pacific climatology, I want to bring you up to speed on that, because a lot of what we're trying to do is actually reconstruct the strength of the Aleutian Low, which is a really important wintertime low pressure system in the North Atlantic that sort of has teleconnections to other climates. So we often measure the strength of the Aleutian Low with this measure, this index called the Pacific North American pattern. And so when you have a positive pattern, you're looking at the pressure. So this is 1981. You're looking at the pressure at 500 millibars. Yeah, 500 millibar geopotential pressure. You've got this really, so here's Alaska right here. This is an anomaly, so you have a much lower low pressure system here during a positive phase. And then you can see that that actually relates to significantly above average temperatures in the western US and really warm temperatures in Alaska, right? Because it influences the jet stream, and you get really cold temperatures in eastern North America. And then really it's just the flip for the negative. Oops, I didn't. Oh well, I changed the title, but I didn't change the figures. This figure sort of shows it together, the positive and the negative phase. So a positive phase, you have a lower pressure, so you have an enhanced Aleutian Low. And so there's the potential for more moisture to make it into the Alaska range, more sea salt, more wind, and then in the negative phase, the opposite, right? More zonal flow and not as much moisture getting into the Alaska range. All right, so there's really two papers, the results from two papers that I want to share with you in the next 15 minutes. So one was led by Eric Osterberg. We were all authors on it, really looking at how you might reconstruct that Pacific North American pattern using something called the North Pacific Index. So what you've got here is you've got the Denali record, and here what we're showing you is the sodium record. So the background here is that if you have enhanced wind and enhanced transport, we would expect more sea salt to make it from the ocean inland into the Alaska range. And so enhanced sea salt would be a representation of an enhanced Aleutian Low, more stronger circulation coming into the Denali area. I've also got another record here. I haven't told you about this, but we also drilled a core up on the summit of Mount Logan. We didn't do it. That was done primarily at the University of Maine and the Geological Survey. And Eric had published a paper previously looking at the North Pacific Index from the sodium record on Mount Logan. And I'll say the Mount Logan record is well dated, but it's not as well dated as our Denali record. And then what they're showing here is just sort of an EOF of those two records that shows the North Pacific Index. And the notion here is that we've seen this significant increase really starting back here in about sort of 1750. We've seen this change in the North Pacific Index, which is an indication that the strength of the Aleutian Low is intensifying. All right, so that's nice, sort of wiggles on a plot, but does it actually match reality? So what we did is we took our index, our proxy index, and we compared it to both sea level pressure, which is sort of the sea level manifestation of the Aleutian Low, and then the 500 millibar geopotential height. And again, this is just for over the period of the instrumental record. So I forget, but it sort of goes back to 1895 reasonable records, really like the mid-1900s of good surface, sea surface and upper geopotential height records. And you can see that we're capturing a significant signal here. So we're correlating the Logan, the average Logan and Denali ice core sodium records, shouldn't be an SLP there, versus sea level pressure on this side and the 500 millibar height. So you can see the sea level pressure, the correlation is really good right in the area activity that's defined by the Aleutian Low. So our conclusion is that our sea salt sodium records are in fact reflecting changes in the strength of the Aleutian Low. And so if I just go back to this first one, is that so our conclusion is that we are in fact seeing this intensification that really starts somewhere in the mid-1700s and continues up to today. So like, what does that mean? Like, who cares about the strength of the Aleutian Low? All right, so that's going to be our next story. So this is work that was published by Dom Winsky as part of his dissertation at Dartmouth. And one of the other things we wanted to do, and really how we sold the proposal, was that we can develop this really high resolution record of how snow accumulation has changed over the course of the past millennium. That's really, after 7 times, we had to narrow in on something that the reviewers could understand. And so this is the work that Dom did. And I've already told you that in these glaciers, as you get deeper in the glacier, right, there's this flow that causes the layers to thin dramatically over time. So in order to actually capture how snow accumulation has changed, you have to somehow figure out how thick each one of those layers was when it was at the surface. So you have to develop a pretty complicated flow model. And one of the hallmarks of this study and the work that Dom did was that he didn't use just one flow model, he actually used 4 different flow models to try and figure this out, and then compared the results and integrated the uncertainty from those 4 different approaches into the results to see how certain we could be in changes in snow accumulation. So the model we like the best is this 3D finite element model that really, there was a whole separate paper written by one of our colleagues using measurements that we taken in the field, right? So we did all that, all the radar so that we could figure out the morphology of the basin. We did lots of measurements on the surface, sort of year after year after year, to measure what the surface velocities were. And we knew what the temperature was because we measured that in the borehole. So all 3 really important for glacier flow. So Seth used that to develop this 3D finite element model using the field measurements. Then there's this kind of classic Glen's flow law in glaciology that relates strain to stress in glaciers. And sort of the bottom line is that essentially the strain increases exponentially as the stress increases. So a little bit more stress gives you a lot more strain. And that stress is really being delivered by the gravity, right? The weight on top of, the weight of ice on top of those lower layers. We went back and looked at a couple of Lonnie Thompson, who's analyzed and done flow models for a lot of different ice core sites around the world. So we just used his models, which are also based on Glen's flow models. And then there are a bunch of 3D flow models that we optimized, knowing what the date at different depths in the ice core was. So we compared all of these. This was a really big effort. We had to do this to get the paper published. We initially just went with the first one. The average of our finite element model up here is actually shown in each one of these. That's the black line. So you can see that the flow model based on Glen's line sort of has lower snow accumulation rates, This one has higher, and this one has higher. But we used all of these to integrate it into our result. So here's the big result on how snow accumulation has changed at close to 13,000 feet on Mount Hunter over the course of the past 1,200 years. So here we are at the present, and here we are going back in time to 800 during the Common Era. The black line represents our best estimate of how snow accumulation has changed. That's a 19-year running average. The gray line represents the year-to-year variability, and the blue represents sort of the envelope of uncertainty that's driven not only by the different flow models that we use, but also by different errors that were made in dating the core. Sort of those 1 to 2 month errors, we were able to measure that, and those are included. So we're highly confident that snow accumulation was somewhere within these two bounds. The upper plot shows you, as I said, for the recent, when the layers haven't thinned much, we can actually separate summer from winter layers. And so that's what we've done up here for the last sort of 140, 150 years. The red represents summer accumulation, and the blue represents winter accumulation. So the big message here that we've tried to get across, and it was picked up by several media outlets when we published this paper, is this is sort of like a hockey stick for snow accumulation that's equivalent to the dramatic increase in temperatures that Michael Mann and his colleagues have published, right? Since the mid-1800s, we see this really significant, big increase in accumulation, and even with the various levels of uncertainty, we are at an accumulation rate that is twice, but it's higher than it's ever been, and if our central estimate is correct, it's twice as high. So instead of 8 to 9 feet of snow accumulation, we're now getting 18 to 19 feet of snow accumulation up there. And we actually know this for a fact, because the first year we put up a 6-meter tower with our meteorological instruments on it, and we lost it. We couldn't find it because there was so much snow. We even had a camera, and we watched the snow build up over it because it was an anomalously high snow accumulation year. The second piece that you pick up from this figure is that most of that increase in snow accumulation, at least over the course of the last 100 years, is coming in winter. We're seeing changes in winter atmospheric circulation that are increasing this, and not really summer. There's a little increase in this record back here in the early part of the century, but really dominated in the latter part of the century. All right, so what's driving this? You might say, well, the world's been warmed by greenhouse gases. Warmer air is able to hold more moisture, so that's driving this increase in snow accumulation. So you can really only count on that for, you know, a little bit of change in precipitation, like sort of 2 to 4% per degree centigrade warming, right? You just can't have a doubling of snow accumulation with a modest increase in global temperatures, even if it's been 3 to 4 degrees centigrade warming in that part of the world. So that might be part of it, but we felt that we had to look somewhere else for that explanation. So we did the same exercise of taking that snow accumulation record and doing correlation coefficients with sea level pressure and geopotential patterns to see what changes in atmospheric circulation might have been occurring. And we got the same kind of result that we got with the sea salt sodium records that we had from the initial core. So when we correlate winter accumulation with, so this is 500 millibar geopotential heights, right? You can see the little triangle represents Denali, and we have these really good, significant correlations, inverse correlations with the Aleutian Low. Much deeper, stronger Aleutian Low, much higher snow accumulation, right? So we have counterclockwise circulation around that Aleutian Low. It strengthens, and we're just driving more moisture into the Alaska Range, and Mount Hunter and Denali are the first big barrier that those air masses hit. So pressure down, accumulation up. So our records would suggest something very similar to what we saw with the sea salt sodium records, that we're seeing an intensification of the Aleutian Low, although this record starts like 100 years later than for the sea salt sodium. We also looked at this, changes in the strength of meridional winds. You can see, so this is pretty big close-up, right? There's Mount Hunter. You can see good correlation with meridional winds right on the east side, east being positive, east side of the Aleutian Low, driving more moisture into the region where the ice core was. Jack made me put this figure in here. We were talking about this today. So we also look at what is the relationship between the winter accumulation on Denali at 13,000 feet and the precipitation records from meteorological stations close by. And we also compared it to summary gridded reanalysis data. So the correlations in the dots are from precipitation stations, and the shading is in the reanalysis. So if you look at the reanalysis, it actually works pretty well, right? We've got this, here's our Denali site, and you can see pretty good correlations with changes in precipitation, right on the, again, on the east side of the Aleutian Low, where that moisture is coming in. So interestingly, you see a lot of sites, so you see a couple of sites, Fairbanks, I'm not sure what that one is, north of the Alaska Range, have inverse correlation, and then several stations on the east side actually have good positive correlations, and then a lot just have no correlation at all. So we're encouraged that at least some of the stations on the east side have good correlations, right? That's where the precipitation is coming in. This is actually encouraging as well because that Alaska Range is the rain shadow, so you wouldn't expect an enhanced Aleutian Low to necessarily be having an impact on precipitation to the north. But it does in Juneau, and that must be Sitka, we are seeing that good relationship. I can't really explain why not all the sites are correlating well, although we know that there's often challenges with precipitation records, and there's also a pretty big difference between what's happening at the surface and what's happening at the mid-troposphere. I just wanted to pick out 3 of the stations on the east side. So this is correlation, number of years of record, correlations between precipitation at the meteorological station and accumulation at Denali on an annual summer and winter layer, and 3 of the stations on the east side, right? Juneau, Kodiak, and Valdez all seem to have pretty good relationships. So there's at least some information that we're representing reality, even though there's some big differences, especially in elevation. So we also wanted to compare this to that Pacific North American pattern that I started you out with. So here we've got the Mount Hunter winter snow accumulation in black. We've got the P&A index, right, which is that measure of essentially the strength of the Aleutian Low, and Kodiak station and precipitation. And anybody that works in Alaska knows that there was this really big shift in the Pacific Decadal Oscillation. You especially know about that if you're working on fish, because Pacific Decadal Oscillation is really linked to sea surface temperatures. A lot of work out of the University of Washington. But we're seeing that shift in the P&A index, but also in the snow accumulation and the precipitation at Kodiak Station. So we're actually pretty confident that we are getting a really good record of changes in the Pacific North American pattern, which the outcome of that is these significant changes in snow accumulation. So a doubling of mass on glaciers at 13,000 feet in Alaska is significant, and certainly significant for ecosystems and society moving forward. And that's happening at the same time that the glaciers at lower elevations are retreating rapidly. So what are the broader teleconnections of this? So we looked at correlations to the tropical Pacific because we know that the Aleutian Low is connected to the El Nino Southern Oscillation and what's happening in the tropical Pacific. So here we're looking at correlations, again, between Denali accumulation and sea surface temperatures. And I think everything colored in the figure, there's a 90% confidence level in terms of the correlations. But you can see, again, sort of, we're going from Denali over here into the Western Pacific and Indian Ocean, and we have these remarkably high correlations. So this is, again, going to be over about 100, 120 years. And so our interpretation of this is that those changes in the Aleutian Low that are changing snow accumulation are actually linked to sea surface temperatures in the West Pacific that affect the energy balance in that part of the region that then actually affects exactly where the jet stream flows. So we're not atmospheric dynamicists. We haven't figured the entire story out, but there's this really intriguing correlation. And when you look at sort of the longer term trend over time between the tropical sea surface temperatures inside this box and the winter Denali accumulation, you actually both have these trends that are pretty consistent over the same time period. And just to take this one step further, we actually sort of brought up a whole set of different proxy records. Here's our Mount Hunter snow accumulation. Here's Hawaii precipitation, which is actually on an inverse scale, because if you expect precipitation in the North Atlantic to go up, actually it should go down around Hawaii. We've got the West Pacific sea surface temperatures, the Indian Ocean sea surface temperatures, and you can see they're all sort of trending up, except maybe the Mount Logan one. So we think we've got this relatively consistent signal across the Pacific. That makes sense. We also wanted to ask the question, well, we're seeing this, but we haven't heard about this anywhere else. We've proven this experimentally, but are the global climate models actually capturing this? When we have this increase in global temperature, do we see the global climate models capturing this regional amplification of the hydrological cycle in and around Mount Hunter? So these are the runs from the GCM North Pacific Index. And this is the GCM warm pool anomaly. So some of the records are getting the warm pool, but none, sorry, I shouldn't say none. 2 of the 7 we looked at capture an increase in the strength of Aleutian Low a little bit, but not a lot. And so we feel that we've found something that's happening within the climate system that is just not being captured in the models. And again, if we're going to sort of have confidence in precipitation regimes that the models produce going forward, we think they sort of have to improve this over the North Pacific domain. So I'll end there. Started a little late, ended not too late. And this is just the group of all my colleagues who, again, it was a really broad collaborative project that made this all happen. I did just want to say one other thing. So we have the several next steps. We've got a proposal in for the second time to NSF to try and develop, look at carbon and a whole bunch of other organic species to track forest fire activity across the Pacific Northwest. And we've got another one that's funded, so we're working on those bottom 10 meters of the core right now. So we're continuing to reap the benefits of having drilled a couple of fantastic cores, and I'll really stop there this time. And happy to answer any questions. So I don't know what's happening to the Alaska current. I suspect it has a connection to the Aleutian Low, that there's obviously what the Aleutian Low is doing is connected with. Anybody know? Anybody an expert? I'll find some people and see what indices. So now is the Alaska current sort of like the Gulf Stream? In the Pacific?
Powerful as the Gulf Stream, but it's an effect of the California current reversing its direction.
Oh, so it's on that side. Okay.
Yeah, it's on the Pacific side, and it's counterclockwise flow over the low.
Yeah, so I don't know. Worth looking into.
Did you go back, I think it was like the last slide about DRL? One of the last.
This one.
Well, it was the one that had a lot of stuff with the sodium. So it's interesting, and maybe you convinced me that the sodium is related to sea level. But back there at 900 years, the sodium is as high in your core as it is now. And there was no increase in accumulation then, between 800 and 1,000 years. So how do you explain that?
I don't. Right. So let's just go forward to the accumulation.
Oh, look, there's nothing there.
Probably a little late, right? Yeah.
I mean, it's not as extreme in Logan, but in the Denali it's the same.
So it's still a little bit low. So the annual annual signal is definitely as high.
Higher.
I got no answer for you, Jack.
Go back to that snow thickness with
snow thickness.
In the ice core,
That part there, what explains the high uncertainty in the almost modern record compared to the low uncertainty 1,000 years ago? Isn't that the gray wiggly?
No, sorry, the gray wiggly lines are the annual signal, the blue is the envelope. So it gets more uncertain as you go back in time because the layers have thinned much more. And the more you have to estimate that relationship. Yeah.
I have like 150 questions, but maybe I'll limit it to 2 right now. The first one is more just technical, and I'm wondering, like, what is the technique for handling the ice cores once they're extracted? Is having some kind of sensitivity to changing temperatures in those cores, even though you're keeping them in that sub-freeze range, and how you go about that. The second one is more related to one of the first comments you made in the process of relating this research back to the local scale, where large-scale changes in Arctic amplification are manifesting themselves at the local level and impacting people. And I'm wondering if there's anyone in this research group or anyone at the New England Arctic Network just kind of wanting to expand this into global disease and all of them, trying to figure out what kind of information, what kind of science can be gained from them, because they really are phenomenal observers of the environment and have a context of environmental change in this realm that was about the past 100 years.
So that's a great question. The first one's way easier. First of all, we just make sure we're really clean when we collect the cores. So we have gloves and masks on so we don't like drool on the cores. It turns out that if you're not drilling a really deep core, the cores are actually really robust. You can drill cores so they shatter, but we're getting better at that. So when you drill shallow core, when you drill deep cores, you have to use a fluid because when you take the pressure off the core, they tend to sort of crack up much more. So the big way that we handle them is we try not to change the temperature of them too much. So you can see we're drilling in tent, we keep them cold, we get them sort of back in the boxes and pack them with snow as quickly as possible. So the snow on the site at sort of 3 to 4 meters is not that different from where they've been. And then we try and keep them at that temperature or a little bit lower the entire time. And these cores for this depth are pretty robust. If you go deeper, like on Greenland, there's this zone called a brittle ice zone that if you actually try to saw or move or touch the cores, they kind of explode. And those cores are left on site for a year to relax, and then they're a little bit easier to handle. So the shallower cores are just, I would say, are more robust in general.
Another thing, though, is that almost everything that you measure is not wiggle sensitive to changes. It's not true that you like gas. Fat gases are much bigger. They have a bigger concern.
Much bigger. And we didn't do a lot of crystallographic studies on these cores, although we are now, but we're looking specifically at melt layers for that. Then your second question is a really good one, and I would say it's a tough nut to crack, but one that we're thinking of is that we've used the term in our proposals that we want to move beyond colonial research, that it's no longer viable to actually go up to the Arctic and do research and not engage the people. So nothing about us without us is a term that we've come to embrace. But we wrote a proposal on a research coordinated network for the North Atlantic Arctic, and the main concern of the reviewers was that we didn't have any really Indigenous voices on our governing panel, even though they acknowledged that our whole proposal was to bring those voices in. They said, well, that's not good enough. You need to start at a much better place so that they're there at the beginning. So with that said, we're essentially reaching out to many of our colleagues who do have viable and deep relationships with different Arctic communities, and we're going to start working with them. And one of our real broad goals is not to just think about the institutions that we can work with, but really the communities. And that's not just in the Arctic, but that's here too, because what happens in the Arctic doesn't stay in the Arctic. So as we think about this in terms of the Gulf of Maine, what's going to happen to our fishing communities? So it's not just about working with the marine fisheries at NOAA, but it's about working with those communities themselves. And so it's a really big lift, and it's really challenging, and maybe in a few years I'll come back and we'll have an answer of how we solved it. I know I've been working with communities in Seacoast, New Hampshire for a decade on the issue of coastal resilience, and we've just got to a point where there's trust and we're able to listen to each other. So I know it's not a 1 or 2 year challenge, it's a long-term challenge. But hopefully we change the nature of the way we do research along the way, and we don't mess the Arctic up like we did every other continent that those of us of European descent have ever found. It's a great question. And if any of you have the answer, please let me know. Go ahead, Tom.
Me or
Yeah, your brain just like, see what I did there?
I don't remember. I'm kind of wondering, you're getting snow accumulation pretty significantly in this part of the world as the Earth is warming. And in much of the other parts of the glaciated world, it's not. It's decreasing. Do you find this similar situations occurring elsewhere on the planet, or is this unique? And is there anything going on the north side of the slope towards the north Arctic that's significantly different on the other side of the mountain because you're blocking sort of what's going on in the North Pacific and the broader Arctic?
So I think it's important to clarify that we're seeing retreating glaciers like almost everywhere, except really the Karakoram, which is interesting, which is sort of the western end of the Himalayas, and I think there's reasons for that. But at low elevation, a lot of the glaciers are retreating. But in very few of those areas do we have long-term records that are of fine enough resolution so that we can do the experiments we did to know what's going on at high elevation. Right? So what we're seeing and measuring tends to be glacier retreat in the snout, and you'd think that that would be closely coupled with the mass input up high, but that sort of takes decades to work itself out. So there could be two different things going on, which is exactly what's happening in Alaska. The glaciers down low are retreating. It's crystal clear. You can see it. Sort of, you go back 5 years later, and they've retreated. You talk to the climbers who say there's roots in the lower part of these mountains that they can't climb anymore because all the ice is gone. So they're retreating down low, and we're getting more snow up high. I don't think we have a lot of records to figure out whether that's happening in a lot of different places. But even in this part of the world, we have our Mount Logan record and we have our eclipse. So Mount Logan record's from close to 20,000 feet. Our eclipse record is from 10,000 feet, closer to the coast in the Canadian part of the Yukon. And we haven't seen this doubling of snow accumulation. So it might be very particular to that location. There is another core about 40 or 50 miles away that's a shallow core. It's like 100 years. That was drilled by the Japanese, and they found this doubling of snow accumulation too. And when we first saw those records, we said, no way. But it fits ours. So they are sort of in the same realm. And then north of that, we don't really have the glaciers to drill records that aren't melted. And so we don't have those high fidelity records. But I would think that it's probably not happening north of the Alaska range. It seems that it's kind of most of it's stopping there. Interestingly, we don't have indigenous stories or big and meteorological data that shows this huge increase in precipitation, right? It's really something that I think so far is a little bit unique, and I'd like to see it kind of replicated in different mountain ranges around the, well, at least tested in different mountain ranges around the world.
Right, testify a little bit on that. A place like the summit, right? So Greenland, for decades it was hard to decide whether to be here or then. The last 2 decades, really clear. Greenland is losing mass, a lot of mass. But at summit, the accumulation going up a little bit. That's in the middle of the ice. But that's probably the thermodynamic, just more moisture in the air.
Right.
But then there is a tendency, there is some, in the last few years, a big concern that the North Slope of Alaska, they are getting a lot of snow, which is bad because it's coming early and it's insulating the permafrost. It's not freezing in the winter. But they think that's probably mostly because of more of the northern Arctic Ocean, not the Aleutian, not the Pacific. So this is really not just driven, right? And so probably is what's going on in the North Slope.
And if that's happening, it's going to make it really hard for them to open up Anwar for drilling, which the trucks are getting ready to roll across as we speak.
Okay, we don't have time to do. I was just going to ask.
I guess that's the last question.
important it was that you did work with like the local community and also people at Denali. What are some of the things that you did to try to strengthen that relationship without just being kind of obviously not just going, I don't know. Like,
From the well, to work in a national park, you have to get permits. So it was clear to us from the beginning, although this builds on our work across Asia and Canada as well, is that it's developing real relationships with them. It's taking the time to develop the relationship. So we talked to them when we were doing reconnaissance fields, like sort of 4 of us skiing around the snow pit, and about our eventual desire to drill an ice core and where they think we should do it and how could we involve the National Park Service. And so that led to lots of different events. We became sort of an attraction in the spring when we went up there. We always did a talk for all the climbers that were out there on global climate change and what was happening to Alaska. Every season when we finished, we always had food left over. So we'd bring out that food and we have a big barbecue at the Talkeetna Air Taxi, which was the company that we always used. And we helped, whenever the rangers needed help, we were there to help. So we helped them put up their tent, but most importantly, we helped them install meteorological stations and shared all of our meteorological data with them, and actually spent the money to do it real time so they could use it for their forecasting. We didn't need it real time, but they wanted it. So we didn't say, well, you paid for it. We paid for it and then provided access to the information for them. So we ended up developing, it was a collaboration. And then sort of along the way, they said, hey, we think you're right. We think Hunter's the place to go. We'll put in time to our supervisors to use the helicopter. And they were very clear. It's that, you know, you are all at the whim of the rescue operation on the mountain. If we have to rescue somebody, we're not going to be able to help you. And we were like, we're fine with that. We had it wasn't a nice plan, but we had an escape plan if we had to get off the mountain, if they couldn't get to us for a month. But we had like lots of food up there to take care of ourselves. So it's about developing real relationships, like nothing new, right? Yeah. Okay, one more.
Just to follow up on the organic portion is, I saw you mentioned something about the worm pool, but there was a phenomenon in the bearing called the cold pool. It's like a surface layer that's been gradually receding over time and drastically changed the extent of Arctic and subarctic fish species. So I was wondering if you had looked at any relations with the cold pool.
Yeah, so I don't, so the bearing, it would be up by the strait, right? North of the Aleutian. Yeah, so interestingly, so we see this positive correlation between, so this, I'm not really answering your question, I'm just trying to see if I can answer it. So this is a relationship between snow accumulation and sea surface temperature. It's not just tropical ocean temperatures, that's one of the biggest. But there is sort of a positive correlation between that and the Aleutian Low, which would, like I would suggest, probably doesn't mean much. So I think the answer, we didn't really explore it in any detail, but we probably could, looking at other potential species. Yeah, food for thought. All right, have a great weekend, everybody.
Yeah, the music. It's like a big deal, yeah.
So, all right.